All right, so with chapter 14, we're going to start to look at what are known as chemical kinetics. And kinetics, when we're looking at in terms of chemistry, is essentially going to be focused on the rate at which a reaction occurs. So how fast does that reaction proceed? But along with that, we're going to see factors that affect the rate, of course. But we're also going to look at what are known as reaction mechanisms. And that'll allow us to see how a reaction takes place. So oftentimes when we look at a chemical equation, we we see the reactants on the left, we have the arrow going to the right, and then the products are on the right. So we're kind of looking at it as just this is what we start with, this is what we finish with. But it's not always just going to be that simple. Oftentimes there's going to be multiple steps that allow us to go from those reactants to whatever the products may be for that particular reaction. In some cases, it may just be one single step, but a lot of the times it's going to be multiple steps, and that's what the mechanism is going to allow us to see. But when we're looking at the reaction rate, again, as how fast does that reaction occur, there's going to be several different factors that influence it. The first one, physical state of the reactant, so essentially what phase of matter are these going to be in. And then with all of these different factors, essentially what we're going to be looking at is how do these influence the number of collisions we have between those different molecules. So we'll see the reactions occur when we actually have those molecules collide. And with the physical state, some states are going to allow for better collisions. So that's why when we look at the chemical equations, we have the formulas there. And of course, we have a balance so that we conserve mass. But in addition to that information, we also put the little subscripts for solid, liquid, gas, aqueous, whatever it may be, because the state of matter for those different reactants is going to influence the reaction rate, as will the concentration. So if we have more of a reactant, we'll see in some cases, it may not actually influence the reaction at all, just based on the mechanism. But a lot of the times, if we have a higher concentration of reactants, we're going to have more collisions. So we'll typically see a faster reaction there. Not always going to be the case, but a lot of the times, as the concentration increases, we'll see the rate of reaction will increase as well. And along with that, we'll see temperature is going to have a similar effect. So if we remember, temperature is going to be a measure of average kinetic energy. Excuse me. Average kinetic energy. So as we increase the temperature, now we're having those molecules move around faster and faster. So when they do collide, we're going to see that they have more energy. That'll typically help have a reaction occur quicker. And then with a catalyst, we'll see exactly how a catalyst works, but again, going to wind up increasing the rate of reaction. And when we look at these reaction rates, the way that we're going to be monitoring it, or the way that we report the rate of reaction, is by looking at the change in concentration over time. So if we look at what we have here, in this case, this could maybe be a decomposition reaction because we're just starting with A, and then we're converting it to B. So in this case, we wouldn't really see collisions. We may be heating it, may light be breaking it down, whatever it's going to be. But you can see these changing concentrations. So we start with 1 mole of substance A and 0 of substance B. And if we think of this as just a liter volume, the mole would just be equal to the molarity. But we start with some A, no B, and then over time, we're going to have some of that convert. After 20 seconds, we have about half of each. And then after another 20 seconds, we've got 70% B, 30% A. So if we were looking at the rate of this reaction, we would just be looking at the change in concentration over some period of time. And when you look at the reaction here, so C4H9Cl, and we're reacting it with water just to make, so butyl chloride, this is going to be butanol. So C4H9OH, just an alcohol, so butanol just because it's got 4 carbons, and hydrochloric acid. The way that we can measure the rate of this reaction is looking at the change in concentration of the butyl chloride. So if we start with an initial concentration of 0.1 molar, and then over time, since that's going to be getting used up, we're going to see the reaction, or we're going to see the concentration, excuse me. We're going to see that decrease. And then based on how much it decreases over time, we can see the rate of that reaction. So if we look at each of these 50-second increments, we could calculate the average rate with those by looking at the difference in those concentrations and then just dividing it by 50 seconds. So that's why we've got the average rate here, molarity divided by seconds, because we're looking at the top in the change in concentration of the butyl chloride over whatever the change in time is. So if we're looking at each of these 50-second increments, the delta T would just be 50, and then the change in concentration would just be the difference between those two. We could also do the same thing with a larger, so we could do 0 to 200 and get the average rate throughout that entire first 200 seconds. But with this one, what I want to point out here is the reason that we've got a negative sign here is because we're looking at how fast the reactant is being used up. So we're going to see a decrease in the concentration. So delta anything is always final minus initial. So if we look at the first 50 seconds, we would do 0.0905 on top minus 0.1. So we're going to wind up with a negative change in concentration there. But the rate is always going to be positive. So that's why we just have a negative sign here, just because this is going to be one of the reactants. And then similarly, we could also look at the rate of formation of one of the products to see the change in concentration of either the butanol or the hydrochloric acid. And we would see roughly the same thing. But if we look at the graph here, we can get the rate at any point of this reaction just by looking at the tangent. So tangent just going to touch the line sort of in one spot. And at that spot, the slope of the tangent is just going to be the rate of the reaction. So there's a couple different ways we can actually find this information based on what type of we can find this rate based on what type of information we're provided with. And then with it, you'll see, if we just look at the tangents here, so at the initial rate, we've got a relatively steep line, so we're going to have a pretty fast reaction to start. But then over time, we start to see that sort of flatten out a little bit. And that's why with the rate at 600 seconds, we don't have quite the slope there, because now this reaction is going to slow down as it progresses more and more. So in this case, we're seeing the rate decrease throughout the reaction here. And that'll be fairly common. But like I said, with the change in concentration for one of the reactants, the reason we've got that negative sign is because we're going to see these reactants get used up. So we're going to have a decrease in the concentration of the butyl chloride. But we could do the exact same thing if we were just measuring the formation of one of these products. We could look to see how much that's changing over time. And it's going to be the same thing. It's just kind of dependent on what one we're looking at. So this would be the rate of disappearance. And then this would be the rate of formation or rate of appearance, as we see there. So depending on if we're looking at a product or reactant, we just want to kind of think about what the change in that concentration is going to be in terms of which direction it's moving. And then with these rates, if we think about stoichiometry, the previous one, if I go back for a second, 1 mole of butyl chloride plus 1 mole of water gives us 1 mole of butanol and 1 mole of hydrochloric acid. So that's why with these, they're just going to be equal. We're just going to change that sign because in this case, it's decreasing concentration. In this case, it's increasing. So that negative sign just makes these equal rather than essentially just opposite signs. But now if we've got a reaction like the decomposition of hydroiodic acid, it's going to produce gas and, or I guess, hydrogen iodide, if you want to call it that too, since the gas. But it's going to produce elemental hydrogen, elemental iodine. But with this reaction, we've got 2 moles of the reactant giving us 1 mole of each of these products. So we want to consider that if we look at the rate of disappearance of this reactant, excuse me, it's going to be twice as much as these are being formed. So when we look at the rates there, we would just want to account for that as well. So that's why in this case, we don't just have the change in HI over the change in T. Now we've got 1/2 of that because this is going to be getting used up twice as fast as these are being formed. And again, that's going to be based on the stoichiometric coefficient we have here. So if we look at any reaction, we can kind of create a general form for it. So just remember with these brackets, that's always just representing concentration. So the change in concentration of A, change in concentration of B, C, and D. And then with it, we want to account for the stoichiometric coefficients. So that's why in this case, we've got 1 over and then little a just for the coefficient, little b for the same thing. And that's why if we go back here, we had a 2 here. So that's why we have 1/2 the change in concentration of HI over the change in T. And then if we go back again, these are really all just ones. So what we really have here is the 1 over 1, 1 over 1. So we just don't really need to write it in the case of a single coefficient. And then we're going to be able to write what are known as rate laws that essentially allow us to calculate the actual rate of those reactions. And the way we're going to be writing it is similar to this. So rate is going to be equal to K, which is just going to be some constant. And then we'll have the concentration of these reactants raised to some exponent. And these exponents are going to be known as orders, and we'll see that in a little bit. But in this case, what the order is, the X order, the Y order. So this means the rate of this reaction is going to be proportional to the concentration of the ammonium ion raised to the X power. Same thing with the nitrite ion raised to the Y power. So if we piece both of those together, the rate of the reaction is then going to be proportional to the concentration of ammonium to the X power, nitrate to the Y power. But to make it that full equation, that's why we add this rate constant K, and that's going to allow us to actually get the rate itself. And then K is going to be specific to individual reactions. And if we just look at a generic one, pretty much the same thing. So K, that rate constant. And then we've got, in this case, A plus B going to C and D. So the rate law would be A to the X to the power, B to the Y. And then with these exponents, X and Y, those are going to have to be experimentally determined. And what we're going to see is in some cases, if it's a 0, anything raised to 0 is just 1. So if it's a 0th order reactant, then the concentration just isn't going to influence the rate at all. But we'll see if it's 1 or 2, then it will impact how fast how fast of a reaction occurs. And like I said, this has to be experimentally determined in order to get those orders. And the way we can do it is by changing the concentration of reactants and seeing how that influences the rate. So we can measure the change in concentration throughout the reaction, and then look at what we started with initially and just sort of compare what we have. So if we look at experiments 1 and 2 here, they each have the same nitrite concentration, so 0.200 molar, but we've doubled the concentration of that ammonium ion. So when we look at the observed rate, we see the rate of reaction doubles. So what that's telling us is that the ammonium ion, the exponent we would have on that is just going to be 1, because when we double the concentration, we double the rate. And then when we look at the nitrite, we're going to have to look at different trials here. So we've got 6 different trials with varying concentrations. We want to look at, if we want to focus on the nitrite now, we want to look at a trial that has the ammonium the same, but differences in the nitrite, just like we did in the previous one. So when we were looking at ammonium, we picked the trial 1 and 2 that each had the same nitrite concentration. So really our only variable was that ammonium concentration. And if we do the same thing with nitrite, we can look at trials 5 and 6. So they have the same ammonium concentration. So now our variable that's going to affect the rate is just going to be that nitrite concentration. And again, when we double the concentration, we're doubling the rate of reaction. So we're going to see both of these reactants are going to be what's known as first order. And that's why when we write the rate law, each of them just have an exponent of 1. Of course, you don't really need to write an exponent of 1. We could just have the brackets here. But just so we can see it, we actually put the 1 in there for the first one here. And what that's telling us is if we double the concentration of ammonium, that'll double the rate of reaction. If we double the concentration of nitrite, we'll see the same thing. Or if we double both of them, then we would have 4 times the rate of reaction in that case. So when we're looking at these exponents, that's what's just referred to as order. So first order, the rate and the concentration are going to be directly related. They're going to be essentially the same. If we double one, it's going to double the rate, but we'll see other orders as well. And like I said, with it, you don't really need to write in the one. But if we have higher orders, we want to make sure we include those overall. But with this particular reaction, since both of these reactants are first order, and we've got two reactants, we would then classify the entire reaction as second order overall. So each of these reactants are first order in the sense that if we double the concentration, it'll double the rate. But if we double everything, now it's going to quadruple the rate. And that's why we would consider this entire reaction to be second order overall. With the overall reaction rate, or overall order of reaction, you can essentially just add up all of the exponents. So in this case, 1 plus 1 just gives us 2. So that's why the entire thing is considered second order overall. And then with another reaction, and if you want to try to practice with this one, see what you can get there, definitely just take a moment to kind of pause it. But again, what we want to do is identify and kind of keep the concentration of one of these reactants the same, so we can see how a change in the concentration of oxygen, for instance, is going to affect the rate. So for the first one, or for this one rather, if we look at trials 1 and 2, have the same concentration of nitrogen monoxide, NO, but we double the concentration of oxygen from 1 to 2. And what we see with the rate of this reaction is it doubles as well. So oxygen is going to be first order. And then if we look at trials 2 and 3, because now in this case, we keep O2 the same. So now when we double the concentration of NO, what we see is the rate of this reaction is actually going to quadruple. So what we're going to see here is the NO is going to be second order, just because when we double the concentration, we quadruple the reaction rate, whereas the oxygen is just going to be first order. So if we were to write this rate law, oops, no, K is going to be, I'm solving for K already. So we'll have, let me do rate. And then we'll have the concentration of NO. But since when we double the concentration of NO, the rate quadruples, NO is going to be second order, and then the O2 is just going to be first order. So the entire reaction overall would be third order in that case, because we've got 2 plus 1 here. And then if you want to, you can write in the 1. But I typically just leave that one out just because it kind of looks weird having an exponent of 1 there. And that gives us the rate equation. But now if we want to actually figure out the rate constant itself, what we need to do is kind of look at the information we have. And if we look, we've got rate, the rate constant, concentration of NO, concentration of O2. And now if we look at this table, we've got the rate, we've got the concentration of each of those. So what we can do is just pick one of these trials, plug in all of this information, and just solve for K there. So if we pick, I'm just going to pick trial 3 just because it's got the biggest rate. I don't like working with small decimals if I don't have to. So 0.227, just a little bit bigger there. So what we can do is take 0.227, plug it into the left. K is what we're solving for. So we'll want to divide everything by the concentrations of these reactants. So we'll divide it by 0.04 squared. And then we'll divide it by 0.02 as well. And what we're going to see is K is going to be a very big number. Let me just pause this to make sure I actually did plug that in correctly, though. All right. Yep. So when you plug it in, we're going to have, I'm not going to pay attention to sig figs for this one, although we've only got 2. So I'll just do 7.1. So I'm rounding this just based on the 2 sig figs we have in these concentrations. But you should get a little bit over 7,000. So it'll be 7.1 times 10 to the third. And then with the rate constant itself, what we have to do is think about the units there. Because on the rate, mole per liter times second. really just molarity over seconds. And then with the concentrations here, now we've got equals to K. We've really got molarity cubed now, just because we've got square of the first concentration and then the concentration of O2 as well. So when we look at the units on K, they're going to be kind of weird. They're going to be dependent on what the order of that reaction is. But since this is third order, what we're going to see, oops, should be -2 there. What we're going to see in this case is the molarity, or the unit there is going to be the molarity to the -2, or you could have 1 over molarity squared times seconds. But with it, the reason we're going to have that is just when we take this rate constant and multiply it by the concentrations, in this case, one of them is squared, that'll give us molarity over seconds. So with the rate constant itself, the units are a little weird, just because we're going to have molarity raised to some negative power divided by seconds there. Unless it's a zero order reaction, then we would just have molarity per second, just because there'd be no concentration piece of it. Okay. And then this is going to be same types of, or similar types of questions, just with a little bit different sort of focus. So in this case, we want to use the data above to determine the rate law for the reaction, the magnitude of the rate constant, and then the rate of reaction when A is 0.05, B is 0.100 molar. So it's going to be essentially the same thing. We just got one additional piece at the end where we're trying to predict what the rate of the reaction is going to be for new concentrations. But just like with the previous one, we can focus on the information we're given to get the order of each of these individual reactants. Then we can just use one of the trials to figure out what K is, so actually solve for that constant. And then once we have K, we have the new concentrations we want to use. We could plug that all in just to get the rate of whatever the reaction is going to be. So in this case, we're just looking at a generic A plus B gives us product C. But when we're looking at it, for the first one, 1 and 2 are keeping concentration of A equal, but they're doubling the concentration of B. But when we do that, we don't see any change in the reaction rate. So the order of reactant B is just going to be 0, 0th order, because the concentration of B isn't going to influence the rate at all. Whereas when we look at trials 1 and 3, so in this case, we want to skip 2 just because B is 0.1 in each of them. And actually, doesn't really matter because B is not going to affect it at all. So if we look at 1 and 3 or 2 and 3, we see the same thing. In each case, when we double the concentration, we quadruple the rate. So this is going to be second order overall, but it's going to be because reactant A is second order, and then reactant B is just 0th order. So I'm going to do the rate law at the top here. Rate is equal to K, and then what we're going to have for this one is only A in there. So if you want to write B to the 0th, you could. But anything to the 0th power is just going to be 1. So that's not going to affect it at all. So we can essentially just leave B out of our rate equation. And then with the second piece, the magnitude of the rate constant, going to be the same thing we did for the previous one. We can pick any of these trials, and now we can know what the rate of the reaction is going to be. We're solving for K, but we have the initial concentration of A. So we can plug all of those, or 2 of those pieces in, and just solve for the third one. So if we pick I'm just going to pick the first one in this case. So 4.0 times 10 to the -5th. And then we're going to divide it by 0.1 squared. What we're going to see is that K will be equal to 0.004. And that makes sense. because this is really 4 times 10 to the negative third, and then we're multiplying it by 1 times 10 to the negative 1 times 1 times 10 to the negative 1. So we get 0.004 for the rate constant. And with this one, what we're going to see is that the unit in this case, since it's second order, we're just going to have the inverse of molarity, or 1 over molarity second, just so that we ultimately get molar per second as our rate unit. And then for the final piece, now we have K, so we know what that rate constant is going to be. Again, this is specific to an individual reaction, and it's also going to be specific to a temperature. But now we have the rate constant K. We know what the concentration of A is. We also know what B is, but that doesn't influence the rate at all. So what we can do is take that rate constant, multiply it by the concentration of A squared, and the rate of reaction then for part C, what you should get is going to be, so what's that, 1.0 times 10 to the negative fifth molar per second. And this also makes sense because if we look at what we have in this trial, or in this table, the first two trials have double the concentration of what we're looking at here. So 0.05 to 0.1, we're doubling that concentration. So we should see the rate double, or rate quadruple, excuse me, because this is a second order reactant. And that's exactly what we see. 1.0 times 10 to the negative fifth is 25% of the rate for trial 1 and 2, because we have half of that reactant there. And again, B doesn't influence at all, just because B is going to be a 0th order reactant. Okay. And then again, if you want to practice with this one on your own, kind of just pause it, give yourself a little bit of time to kind of work through it. And when we look at this reaction, now we've actually got real substances rather than just A, B, and C. But in this case, NO plus hydrogen gives us nitrogen gas and water vapor. And then they did this trial, or did this experiment with 3 different trials, changed the concentration of both of those reactants, measured the change in rate, or measured the change in concentration, I should say, to get the rate of these reactions. So again, we want to get the rate law, determine what K is, and then actually figure out what the rate of this reaction is going to be if we had these two concentrations. So if we look at trials 1 and 2, NO is staying the same. H2 is doubling though. And when H2 doubles, we see the rate doubles as well. So H2 is going to be first order. And then when we look at trials 1 and 3, they're keeping H2 the same this time. When we look at trials 1 and 3, NO doubles. And what we see with the concentration is that quadruples. So the NO is going to be second order. Hydrogen is going to be first order, which means this reaction rate overall is going to be third order. So when we write the rate law, we'll have the rate equal to K times the square of the NO concentration, that nitric oxide concentration, times just the concentration of hydrogen, H2. So again, it's third order because the nitric oxide is second order, hydrogen's first order. So 2 plus 1 just gives us 3, third order overall, excuse me. And then just like the previous ones again, if we want to figure out exactly what that rate constant is, we can take any of these reactions. I'm going to take the third one, so we can do 4.92 times 10 to the negative third, or 0.00492, divided by the concentration of hydrogen, since that's just first order. And then we can divide it by the square of the concentration of nitrogen, since that's second order. And what we see when we do that is K. Oops. K will be 1.2. Uh, 1.2 times soup, and actually it'll just be 1.2. Oops, that was the eraser. And then with the units again, just like the third order one we saw before, means we'll have molarity to the negative second over seconds, or you could also write this 1 over molarity squared times seconds on the bottom like that. Either way represents the exact same thing. But now when we look at it, the reason, again, this gives us mole per second is because this is the unit on K. Nitric oxide is squared, so we've really got molarity squared, so 1 times molarity squared. And then with the molarity of the other reactant, just first order, when we look at what actually occurs here, if I change the color, molarity squares canceled. 1 doesn't really affect anything, so we just wind up with molar per second, I should say. And let's see the unit we have for these rates overall. And then for the final piece, we've got the rate constant now. We've got the concentration of each of those reactants. We can plug all that information in to see what the actual rate of the reaction is going to be. So if we do 1.2 times 0.2 squared, oh, actually, I was looking at the third trial. Whoops, we want to do 0.05 squared. And then we'll multiply it by 0.15 for the hydrogen. And what we're going to see in that case is we get a reaction rate of 1.4. Oh, that was not even close to what I was reading from my calculator. So it's going to be 10 to the negative fourth. So 4.5 times 10 to the negative fourth meters, molar per second, excuse me, I almost said meters. And when we look at this one, it makes sense why that's going to be. Because if you look at the concentration of hydrogen, kind of in between what we have here, but the concentration of nitric oxide is lower than what we have in any of these three. So the overall reaction rate makes sense that it's going to be lower than any of these. It's going to be slower, I should say, just because the concentration of this nitric oxide is going to be a little bit less there. And especially since we're squaring that one, that's going to have more of an influence than just the hydrogen, which is first order. Okay. And then with it, we'll wrap it up with just that last example for this first video here.